All right, Honors Chem, not Gen Chem, Honors Chem. We are going to continue on with our discussion of enthalpy, and we're going to talk about enthalpy of formation. So formation means making something. So this is the heat or the energy that it takes to make something. So let's define this. So the enthalpy, and remember enthalpy is just a form of energy, okay, required or sometimes even released to make, or when 1 mole of a compound is made or formed from its elements. Okay, so it's the amount of energy either required or released when 1 mole of a compound is made from its elements. Okay, so that is what delta HF is, and that's the symbol that we use for the heat of formation or the enthalpy of formation. So let's look at a couple of examples and how we use this. Okay, so the heat of formation for nitrogen monoxide is a positive 91.3 kilojoules per mole. So that means, since that positive 91, that means I have to put that heat into this reaction. So that means this is endothermic. Heat or energy is absorbed. So this is endothermic. So if I have a positive delta H of formation, this is endothermic. Okay, I have to put energy into this reaction. And notice we are making this from its elements, and we are making 1 mole. We are making 1 mole. So 1 nitrogen, 1 oxygen constitutes 1 mole of nitrogen monoxide. Now, because nitrogen and oxygen are diatomic normally in their elemental state, we can only use 1/2 of a nitrogen mole and 1/2 of an oxygen mole. So this is where we actually can use fractions when we balance equations, because when we do a heat of formation, we only want to make 1 mole. And if they elementally come in groups of 2, do you guys remember the elements that come in groups of 2? Yes, Brinkelhoff. So we have bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine that all come in groups of 2. So we have to remember those Brinkelhoff elements, and when we need less than 2, we're going to have to put a fraction in front of them. Okay, so that's going to take 91.3 kilojoules per mole to make nitrogen monoxide. So nitrogen monoxide takes more energy than just plain nitrogen or plain oxygen. Okay, so hopefully this computer will let me start writing. Okay, what would the energy absorbed of 2 moles be? So if I have 2 moles, wouldn't I multiply this by 2, this 91.3 by 2? Yes, I would. And we are going to use unit analysis to do that. So let's fill in our Brinkelhoff elements really quick. And yes. I am getting really frustrated. So we have bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So please watch out for those, okay? Now, let's do our 2 moles. So we're going to start out with our 2 moles of nitrogen monoxide. And we know that this equals 1 mole being formed. So I can use this equivalence. So 1 mole of nitrogen monoxide being formed is a positive 91.3 kilojoules. So if I multiply that by 2, because my moles cancel out, that will give me 182.6 kilojoules for that reaction of making 2 moles of nitrogen monoxide. Okay, so here we go. What's the heat of formation of methane? It's a negative 74.6 kilojoules. So notice this is a negative value. Let's highlight that. That's a negative value. That means energy is released. This is an exothermic reaction. So if I have carbon and hydrogen, the energy of that is up here. And when I make methane, it actually goes to a lower energy state. So that means 74.6 kilojoules of energy is released. And if it's released, we have a, did you guess it? Exothermic reaction. So if I have a negative heat of formation value, I have an exothermic reaction. Okay, so here we go. We have carbon plus 2 hydrogens. Notice we needed to get 4, and each hydrogen has 2 in there, so we're going to need 2 of them to get 4 individual hydrogen atoms. That gives me a negative 74.6 kilojoules. So this is going forward. What about being decomposed? Doesn't that mean the reverse? Wouldn't this be hydrogen breaking down into carbon and 2 hydrogen molecules? Compare these 2 reactions. Isn't one the reverse of the other? So what happens to the delta H, or the enthalpy of the reaction, when I reverse it? Think about that. Do you have any idea? Yes, I take the negative value. So the delta H of this would be positive 74.6 kilojoules. Okay, so the reverse reaction just has the opposite sign of that energy. Okay, so I want to know how much it would be when 2 moles are decomposed. So I'm going to use my unit analysis here. So if I can use this as 1, that equals 1 mole. So if I have 2 moles of methane being decomposed, I know that 1 mole of methane being decomposed is a positive 74.6 kilojoules. So I'm going to cancel out my moles of methane, and 2 times 74.6, that gives me positive 149.2. For the decomposition, remember we are going backwards, the decomposition of 2 moles of methane. So remember that the reverse reaction is just the negative of the forward reaction. Okay, it's just that negative of the forward reaction. Okay, so I want to look for the delta H of formation for methanol. It is 238.7 kilojoules. I want to write the reaction showing the formation of 1 mole. So if I have, oh boy, this put me all the way to the beginning of the book. Let's get back to where I am. Okay, so I have 1 mole of methanol. So I'm going to just put methanol as my product because that's what I'm making. I'm making 1 mole. So let's look at the elements that are in methanol. I've got carbon, I've got hydrogen, and I've got oxygen. Now, in elemental carbon, it does come individually. So I can just write 1 carbon. Hydrogen, though, is one of our Brinkelhofts. It's a diatomic and oxygen is also a diatomic. So elementally, they come in groups of 2. So when I add hydrogen, I need to add H2. And when I add oxygen, I also need to add O2. Now, the thing that we need to think of is how many of each of these atoms do I need to make one thing of methanol? So I need 1 carbon. I need, let's see, 4 hydrogens. Can I get 4 hydrogens out of groups of 2? I can. I need 2 H2s to get me 4 hydrogen atoms. Okay? And then I have 1 oxygen. How do I get 1 oxygen out of a group of 2? I have to multiply it by 1/2, right? 2 times 1/2 is 1. So I need 1/2 of these. So my coefficients are going to be 1 carbon, 2 hydrogens, and 1/2, or you could also do 0.5 oxygens, will get me 1 mole of methanol. Okay? And then over here on the right where I put my tally, we would put the delta H being a negative 238. So we would do delta H equals negative 238. It doesn't want to let me write. That's not what I want to do. Negative 238 kilojoules per mole. Okay, so we would put the kilojoules right there. All right, now let's go down to this. Now here's a heat of formation table, and we are going to put a heat of formation table on your homework, and I've already linked a heat of formation table for your homework. And I just wanted to show you a couple of things here. I wanted you to look over this. So silver is 0, bromine is 0, chlorine is 0, calcium is 0. What are you noticing that are the same for all these things that have 0 heats of formation? They're elements. Elements have no heat of formation. Okay? So when you have an element, the heat of formation is 0 because we can't make elements. They're already here. So the heat of formation for elements is 0. So we use this heat of formation for compounds. So when we are making compounds, this is what we use. We're going to use heats of formation to find compounds. Elements by themselves are always 0. Okay? So we're going to use this heat of formation in our heat of formation table to have you look up values and create equations like this, where we are creating compounds from the individual elements. Okay? I'm going to have you create equations going forwards and backwards. Remember, backwards, the heat of formation is just the negative value. Okay? So have a good time doing this, and then next time we're going to start using Hess's law, which is a really interesting way of using this table to figure out reactions that we can't really do in the lab. All right? So have a great time. We'll talk to you later. Bye.